The following video is on the extreme values. We will say that a value x equals c is an absolute maximum of f of x if f of c is greater than or equal to f of x for every value of x. In other words, if the y value is greater than or equal to all other y values that the function achieves. We will say that a value x equals c is an absolute minimum of f of x if f of c is less than or equal to f of x for all values of x. In other words, if f of c is less than or equal to every y value that the function ever achieves. In the picture above, we see that the absolute max is at b and f because those are the two largest y values that this function ever achieves. Similarly, the absolute min is at e because this is the lowest y value that the function ever achieves. We will say that a value x equals c is a relative maximum of f of x if there is an interval I such that f of c is greater than f of x for all x in that interval I. Notice that I'm using the cursive I here. We will also say that a value x equals c is a relative minimum of f of x if there is an interval I such that f of c is less than or equal to f of x for all x in I. So what each of these are saying is that we can look at an interval I and that x value will be a maximum or a minimum on that interval. So for example, d is a relative maximum because on the interval I that I drew here, you'll see that d is the largest y value that's achieved in that open interval. Similarly, e is a relative maximum because, b is a relative maximum because in the interval that I drew here, b is the largest y value that's achieved. Notice that f, however, is not a relative maximum because we can't draw an open interval around it. Similarly, I could draw open intervals around c and e as shown in the picture, and we see that c and e are now relative minimums. A is not a relative minimum because we can't draw an open interval around a because it's an endpoint. So the relative minimums are at c and e. So how do we find extreme values? Notice that I've marked off extreme values in these cases, and in each case the extreme value either happens at an endpoint or when the derivative is 0, I've marked off the horizontal tangent lines, or in the second picture when the derivative does not exist. Here we have a cusp. If x equals c is a relative extrema, then f prime of c either equals 0 or does not exist. Warning, not all the values x equals c, such that f prime of c equals 0 or does not exist, will be relative extrema. We need to be careful. Furthermore, remember that endpoints are not relative extrema. We only look at endpoints for absolute maximums and minimums. To summarize the warning in a Venn diagram, the relative extrema are a subset of the values where the derivative is equal to 0 or does not exist. An example of this is f of x equals x cubed. Notice that f prime of x is 3x squared, and this equals 0 if x equals 0. But notice that on the picture here, even though we have a horizontal tangent line at x equals 0, it's not a relative maximum or minimum. We will talk about points like this as we move on. Another example would be the point f of x equals 1 over x. f prime of x equals negative 1 over x squared, which we know does not exist if x equals 0. But once again, at x equals 0, that value doesn't even exist on the graph. So, of course, it's not a relative maximum or minimum. we will say that the value x equals c is a critical value for f of x if f prime of c equals 0 or does not exist. So what we want to do if we're trying to find extrema is find all the critical values and then test whether they're maximums or minimums. We also have the extreme value theorem. The extreme value theorem says that every continuous function f of x attains both an absolute maximum and absolute minimum over any closed interval from a to b. So just to verify this theorem for ourselves intuitively, let's look at continuous functions over the interval from a to b. So here I connected the two dots between a and b with a continuous function, and notice that at c I have an absolute max, and at b I have an absolute min. Remember, for absolute extrema we are allowed to use the endpoints. We could try this again. Here I've connected a and b with a little bit more crazy function. It's still continuous though. And we still achieved our absolute max and our absolute min. Finally, we could also connect the 2 points with a straight line. Notice in this case, every x value is both an absolute max and an absolute min. So how do we find absolute extrema on a closed interval? Well, step 1, we want to take the derivative in order to find our critical points. Step 2 and 3 involve taking those critical values and plugging them in to find the y values at those points. We also need to test the endpoints to find absolute extrema, so step 4 is to find the y values of f at the endpoints. Step 5 then says that the largest y value will give us the x value that has the absolute max, and the least y value will give us the x value that gives us the absolute min. So for example, let's find any absolute extrema of the function f of x equals 5x squared minus 10x minus 1 on the interval from -2 to 5. The first step is to take the derivative, so we get 10x minus 10. We want to find the critical values, so we set the derivative equal to 0, so f prime of x equals 0 when x equals 1. Notice that the derivative always exists, so we don't have to worry about critical values where this derivative does not exist. Our only critical value in this case is 1. Now we create a t-table. We're going to compare the critical values and the endpoints to their y values. We have 3 values that we're testing, -2, 5, those are our 2 endpoints, and our critical value 1. We plug in for the y values in each case into the original function, and we're left with 39 for -2, -6 for 1, and 74 for 5. We notice then that the least y value happens when x is -1, so the absolute min is at 1. The greatest y value happens when x is 5, so the absolute max is 5. Let's try it again. Let's find the absolute extrema for f of x equals x plus 1 over x minus 1 on the interval from -3 to 0. We have to take the derivative using the quotient rule, so we end up with -2 over x minus 1 squared. We now figure out when this derivative is equal to 0. Notice that this never happens because the numerator will never be equal to 0. The only time a fraction can equal 0 is if the numerator is equal to 0. This fraction does, however, not exist when x equals 1. So we have one critical value when x equals 1. Notice, however, that 1 is not on the interval that we're interested in. We're only interested on the interval from -3 to 0. So we can actually ignore 1. The only the only values that we need to test are -3 and 0. We plug these into our t-table and plug the values into the original function. When I do that, -3 gives me 1/2 and 0 gives me -1. So we see that we have an absolute min, the lowest y value, when x is 0, and an absolute max, the largest y value, when x is -3.